Okay, so we move on to the next talk by Tista Banerjee. She's going to talk about entanglement transitions in Fluke systems.
So, good afternoon. First, I would like to thank the organizers for giving me this opportunity to present our work here. So today I'm going to talk about entanglement transitions in integrable non-Hermitian Fluke systems. And this work is done in collaboration with my supervisor, Professor Krishnendu Sengupta. So I will try to describe all the terms as we go along. So first I will describe the physical setup of the problem. So we have a quantum system, and then we are pumping energy to the system, and it is subjected to continuous monitoring. So due to this continuous measurement, there will be some measurement back action which feedbacks to the system, and this will lead to non-unitary evolution for the system's fields. So one possible description, if we want to describe this system properties using a Hamiltonian description, so one possible description would be an effective non-Hermitian Hamiltonian. So, but for more general description, one should consider the full open quantum system, where one considers the system degrees of freedom and then the Barth degrees of freedom and the coupling between them. And this, for a more general setup, in some regime, one can do this evolution of the system density matrix by this Lindblad master equation. In terms of this trajectories, quantum trajectories, this effective non-Hermitian Hamiltonian could be if we post-select all the trajectories, then one that would have no jumps. You can consider the dynamics of that quantum trajectories could be explained by this effective non-Hermitian Hamiltonian. For this talk, I will mainly focus on this non-Hermitian Hamiltonian. So. So for describing this kind of setup, we will consider a very simple model Hamiltonian, which is a transverse field Ising model. And this is non-Hermitian because the transverse field now is a complex parameter in the system. You can see that because of this dissipation present, this gamma here, if you start from any initial state, system will eventually evolve and will reach to a steady state that will be controlled by the least negative imaginary part of the complex energy. This Hamiltonian has this pair spin flip terms. So because of that, the total magnetization is not conserved. The spin parity is conserved. And we are using this Hamiltonian because it is via Jordan-Wigner transformation can be mapped to a bunch of non-interacting free fermions, and one can do a lot of analytical calculation here and understand the entanglement properties of this system. So previously there is a paper by Lee and Chen in 2014 where they have shown that this steady state can have interesting phases if you tune the parameters and can lead to interesting quantum phase transitions in this kind of setup. And later in 2023, there is a paper by Tarkishiansky who showed that if you quench this kind of, using this kind of Hamiltonian and initial state, then depending on this dissipation, one can have interesting entanglement scaling properties of the steady state. In the low dissipation regime, there is a logarithmic scaling, but in the high dissipation regime, one can have this area law entanglement scaling. So in terms of entanglement scaling, there could be interesting transitions in the steady state. And what I will try to describe in this talk is that if suppose you make this like magnetic field time dependent and you consider different type of periodic drive protocol, can we get an interesting entanglement transitions because we have now frequency as a tuning parameter. So, here we will consider mainly this continuous drive protocol and square pulse drive protocol, and we will see that the entanglement scaling properties qualitatively are same for both of these drive protocol, only the quantitative like transition points and other shift. So just I will quickly go through what kind of entanglement measure I will use. So I will mainly use this bipartite von Neumann entanglement entropy. Suppose you have a chain and you divided it into two parts, then A and A bar, the total Hilbert space is just a direct product of the Hilbert space of A and Hilbert space of A bar. Then given a state psi, you define your subsystem, and you can calculate the von Neumann entanglement entropy between the system subsystem A and the complementary part of it by this equation. And this reduced density matrix of the subsystem A, rho A, is just one can obtain by tracing over the degrees of freedom of A bar of the full density matrix. So one important thing is for a subsystem size of small l in this kind of spin-half systems, to get this von Neumann entanglement entropy, one need to like diagonalize a 2 to the power l cross 2 to the power l matrix. But due to this free fermionic nature of this model Hamiltonian, there exists special tool to find the spectrum of rho A. One need not to consider all this 2 to the power L cross 2 to the power L matrix, but one can do it by polynomial size matrix diagonalization in this kind of setup. So, suppose you drive the system with really high frequency, then one should reproduce the result of the Quench setup in this kind of problem. So here I am considering a large drive frequency, and all the other parameters are fixed. Then you can see as a function of this dissipation rate gamma, here we have plotted the coefficient of the logarithmic term. So here is the half chain entanglement entropy as alpha log L by 2 plus beta, and if you see alpha as a function of gamma, you can clearly see there is a entanglement scaling transition from a logarithmic to area law as you increase your dissipation rate gamma. And so the different symbols here is that one is the exact numerics calculation. What you can do, you can calculate the evolution operator by some tautorization technique and compute the steady state after very large stroboscopic time, and then compute this von Neumann entanglement entropy of that steady state. And then these blue crosses are from a perturbative treatment of the Floquet Hamiltonian. So you have this periodic drive, and the system will eventually can be described due to the Floquet theorem by an effective time independent Hamiltonian. And if you do some kind of perturbation theory in some appropriate regime, in the high drive amplitude regime particularly, you can construct an order by order effective Floquet Hamiltonian, and the second order effective Floquet Hamiltonian follows the numerics very well. And then this green curve is an exact like analytical construction of this entanglement transition where one would employ the free fermionic nature of this problem, and then can do a first order Floquet Hamiltonian calculation and try to see what is the momentum space correlation function. What is the singularity structure of that correlation function? Then employing that singularity structure, one can do some analysis and get this kind of analytical curve there. And you can see it can very well capture the transition point. So this is the physics in the high frequency regime, and it is similar to that of a quench problem. So now the question we would ask from here, that if we lower our frequency, can we get what kind of entanglement transition we can see? Can we get a much richer structure of the entanglement phase diagram in the plane of dissipation and frequency, because now frequency is a tuning parameter. And the second question is, suppose you lower your frequency. So as you are lowering your frequency, you are getting more and more, like time period is high. So you are getting more time, the system is getting more time to adjust with the drive, and the Floquet Hamiltonian will become more and more non-local in the low frequency regime. So can we get an system size, I mean subsystem size dependent volume law there? Though the volume law will not be present in the thermodynamic limit because of this infinitesimal dissipation present here, but can we get something, some finite size effect there? So first thing is that if you tune your frequency, so you can see that this is the entanglement phase diagram. You can say that this is the dissipation rate and this is frequency. So you can see there are reentrant entanglement transition from a logarithmic, this red one is the logarithmic scaling, and this yellow one is the area law scaling of the entanglement entropy. But you can see there are reentrant transition, and there are several frequencies where there is no, no logarithmic scaling properties. So what are those frequencies? If you do the perturbative analysis, you can show that at those special frequencies, there is some emergent conservation law. So your original Hamiltonian doesn't has this total magnetization conservation, but as you start driving this system at special frequencies, you can get an emergent magnetization conservation. And that magnetization conservation leads to area law scaling of the entanglement entropy. So these are the frequencies where there are some emergent conservation. If time permits, I will just go through the Floquet structure of the Floquet Hamiltonian. And if you look at the singularity structure of the correlation function, you can say here there is this singular correlation function in the momentum space, and in the area law scaling, there the correlation function becomes smooth. So you can attribute that to these different scaling properties of this this Hamiltonian. And this is for continuous drive protocol, and this is for square pulse. You can see qualitative features are same if you change your drive protocol. So now the second question, that whether we can get effective volume law because we are lowering our frequency, and the Floquet Hamiltonian become more and more non-local there. So here you can see that in the high frequency regime, this is a range of interaction of the effective Floquet Hamiltonian. In the high frequency regime, this is just a this is the difference of the distance of the sites, and this is the interaction strength. In the high frequency regime, you have this nearest neighbor interaction in the effective Floquet Hamiltonian, and as you lower your frequency, your effective Floquet Hamiltonian becomes more and more long ranged. And now suppose you choose your subsystem size somewhere here, you can then say, okay, my effective Hamiltonian is long range, and you can get a volume law entanglement there. But as you choose your subsystem size much higher than this, your system will see an effective short range interaction, because long range is a relative thing, and then you can see a crossover to a logarithmic scaling. So this is log L, the subsystem size, and this is the entanglement entropy of that subsystem size. So you can see there is a volume to logarithmic law crossover in the scaling of steady state entanglement properties. So, so this is can be attributed to this long range structure of the Floquet Hamiltonian. So the thing is, in the thermodynamic limit, you cannot get a volume law because of this dissipation. But if your subsystem size is finite, you can have a strong finite size effect here. Okay. So this is the result, and okay, I have still 4 minutes left. So I would first discuss some like open questions in this direction. The first would be that what happens if you have these quantum jumps there? So which regime of this phase diagram will remain same? You can show that in the high frequency regime and low gamma regime, you can have this entanglement transition. So you can access at least one high frequency, this one emergent conservation here, and maybe as you lower your frequency, this thing will be not there. So one, that question. And the second is, if you see this Hamiltonian, what we have done, suppose you have a transverse field Ising model, you do a repeated measurement, and then you like define this Hamiltonian by using from Lindblad master equation. So you derive this effective non-Hermitian Hamiltonian, and then you drive it. But the more I think the correct way to do this is that you have now two time scale. One is the rate of measurement, and another time scale is the rate of driving of your system. Then to really go to a full open driven quantum system and to approach this effective non-Hermitian Hamiltonian, you have to consider these two time scale and see how from there one can reach to an effective non-Hermitian description. You have to consider the interplay of both the time scale of measurement and the time scale of drive altogether. So these are, I mean, these open questions I would like to answer like in the future, in my future research. So So I will quickly go through the structure of the Floquet Hamiltonian. So this is some technical thing that you have this 1D transverse Lie chain. By Jordan Wigner, you can map it to the free spinless free fermions. And then for each, you can see that only k momentum k will be coupled to minus k, and all the other momentums are decoupled from each other. So for each momentum k, you have this two-level structure. But now it is time dependent. So you can calculate the evolution operator for every stroboscopic time. So for a stroboscopic time of a drive of time period t, you can calculate this evolution operator, and then you can do a certain kind of perturbation theory, where you consider the high drive amplitude, and 1 over that drive amplitude is your perturbation parameter. You can do some time dependent perturbation similar to a perturbation theory, time dependent perturbation theory interaction picture, and you can construct this first order effective Floquet Hamiltonian. Now you can see this is the structure of the first order effective Floquet Hamiltonian, where alpha k delta k are function of some cos k sin k. And then the off-diagonal off-diagonal elements are modulated by the Bessel zero function. So Bessel zero is a function which has certain zeros. So if your frequency hit those zeros, your off-diagonal term vanishes, and the first order Floquet Hamiltonian commutes with magnetization. And this is the emergent conservation law that I was talking earlier. And as you incorporate higher order perturbation theory, there are other Bessel modes which starts controlling your dynamics, but still this is suppressed by 1 over frequency, and higher order will suppress more by 1 over frequency to the power, some power, depending on your order of perturbation theory. So in the high frequency regime, you can still say that dynamics can be explained by this first order Floquet Hamiltonian, and because of that you can see those special frequencies here, where you have only areal or entanglement scaling throughout the dissipation rate. So yeah. So this is the calculation of the entanglement entropy. You have now a two-level system for each momentum mode. You can calculate the different correlation function here. Only there will be, due to the Gaussianity of the state, you will have this three correlation function. And by this correlation function, you can construct a 2x2 correlation matrix in the momentum space. By doing this Fourier transform, you can generate this block Toeplitz matrix, where has this block like Toeplitz matrix structure. Each diagonal are same, but it is now a matrix symbol. Each element is itself a 2x2 matrix. Now you can say that your entanglement entropy can be calculated by calculating the eigenvalues of this matrix, and the spectrum of reduced density matrix can be computed by combinatorics. So using this and this structures, we have done this analytical analysis and capture the transition analytically. So with this, I would like to thank all of you for listening. Thank you.
Questions?
So you showed that in the gamma going to 0 limit, this alpha became 1/3. Is that just the static? Yeah, I mean, it's going to this 1/3. I mean, is that just the static factor?
Yeah, I mean.
But you still have driving, so
yes. So because you cannot reach to this structure like smoothly, gamma equal to 0 and gamma equal to non-zero, you have very like gamma equal to 0 is a unitary evolution, gamma equal to non-zero is not a unitary evolution. But it turns out that its factor is similar to that of a static 1/3 log L.
It's not obvious it should.
Yes.
Okay, so since there are no more questions, so let's thank the speaker again. Yeah, thank you.